Yeah, thank you very much for the kind invitation to give some of my knowledge, which is left of my career here in Prague. Thanks to Professor Marquardt to inviting me and giving me the opportunity to tell a little bit of what in former times we and myself have believed to have understood. And it's also a pleasure to see a good old friend from my amorphous silicon period. It's like Chagall with the blue, or Picasso with the blue, or the naturalistic, or the red period. So Jan is here of my amorphous silicon period. The next I'd like to say is that you don't need to read all the items which are on the slides. And if you are interested, you could have a copy of what I'm showing to you here. So you could relax and lean back. And the next is, don't even think to try to read all the numbers and all the equations. I will go through very, very quickly and tell you in a nutshell what it is. So instead of sticking to the title, I will try to convince you that the light that comes out of a solar cell, of an illuminated solar cell, will tell you about the quality of the cell. And the light that comes out of a part of the solar cell, of the absorber, will also tell you what's the quality of this later cell if you make the technology of this. That means the light is the language of the matter. This is an old Ondi, one of my professors. The light is the speech of the molecules, and the light is the speech of the matter. So what I'm going a little bit through the basics very, very quickly in some more sort of easy sketches, and tell you what one could see when you apply this knowledge. And all what I'm saying is physics, a little bit semiconductors, and nothing else, and a little bit optics. So what we see is here, it's the light, the spectral light flux that comes out of matter from this little green piece. It comes under a certain solid angle, and the matter has a particular temperature and the particular chemical potential. And this here is nothing but the Bose distribution in the Planck's law, and this is the energy, and this is a constant. There is H-bar and pi and those things, and this is the emissivity, and the emissivity is the same as the absorptivity, because if not, then spectrally, if not, then the second law of thermodynamics would be violated, and we don't even try this. We like not to get this. So the mu photon is in the semiconductors or absorber, the splitting of the quasi-Fermi level, and this gives the maximum achievable open circuit voltage. Is this the ability to give work out of this system matter? Sorry. The other one is in semiconductors or in molecules, you get a transition from the ground state to the excited state, for example here, and then you get a fast relaxation in K and in energy. And for those who know semiconductor physics, the relaxation time for the K space and for the energy are different. So this gets faster than this here, and this is in general so. And if the recombination needs longer than this relaxation, then you see this excited state by light that comes out from transitions from here to here. For the balance of the absorption and the emission, we need the absorption, ground state, final state, the spontaneous, and the stimulated emission. And if there is some addition transition from the upper level down, then this reduces, this here, non-radiative, then reduces the number of carriers here, and then we get less light out. So this is the algebraic gymnastics for this. This is absorption, this is stimulated emission, this is spontaneous emission. You see this, and this is symmetric because there is the photon density in, and the bastard of this of these relations is the spontaneous emission. And the level occupation for the ground state and the excited state is the conduction and valence band. This is by quasi-Fermi levels. And charge neutrality, we get valence band and conduction band for the electrons in the hole, respectively. So this is nothing but some equations that tell you the ups and the downs of these transitions. What we see is this flux that comes out. I already have shown this. This is this equation, and then we get the mu photon. And I hope that some of you know what the chemical potential of that stuff is. We'll show you some very fast example. This is the photon flux from a thermal emitter, graphically like this. It's photon energy versus photon flux. If we put in the emissivity or absorptivity and say this is artificially zero, once more, artificially zero here in the low band gap, and here then we have to multiply this function by a rectangle. The next is we put some more realistic density of states in, then we get something like this. And now we switch on the chemical potential, and it's got like this. If the chemical potential is positive, then we get a large emission from this stuff. And the funny question would be, if the chemical potential is negative, then we get less out. Then we get less out than the thermal balance that is predicted by Planck. And you could ask me the question how to do this. Okay, next is, this flux in a logarithmic plot tells you on the left-hand side, on the left-hand side, the absorption. This is weak absorption. Here is very, very strong absorption. You forget about this one, and then you get this equation up by a minus sign, and the slope here in the log plot over the energy gives you the temperature. And the magnitude here gives you the chemical potential. So you could set what is the most accessible work that could be extracted from this. And this is defined by this splitting of the quasi-thermal levels of the electrons and the holes. This is the whole story. Now we do this. Regularly, we shine on the absorber, we shine light from the sun. We could do it also by a lamp, or by a laser, or by a candle. And if you would succeed in doing the excitation by a hammer, you could do it also by a hammer to put the electrons from the ground state to the excited state. Regardless how you do it, you get some inversion of the occupation in comparison to the thermal equilibrium state. Now, the matter consists of plenty of these little things, and you have to take all these into account, and you make this optical experiment with all these forth and back from the absorber, and you have some substrate also for the absorber. Then you have to regard this zigzagging for and both, and so on. And then you end up with some equation which you should not even try to read. This is nothing but the result of algebraic gymnastics for the matrix transfer formalism of these three layers. Or in principle, it's a 5-layer system. This is 1, 2, 3, 4. Oh, it's a 4-layer system. Sorry for that. And if you include this substrate, then you get an additional expression here. And what we did not consider for this relation, this is photon recycling, which is in the most cases not necessary. So the excess carrier density gives the generation of the photons. And here you see some calculation. How does it work with the excess carrier density? This is the normalized thickness of a sample with different recombination velocities, and the excess carrier densities looks like this for different cases. Here at the rare surface there is recombination velocity 0, here it's very high, and here is a normal one, and we get the luminescence out from these different depths of the centers that give the light. Looks like this. Again, you see here the slope, the temperature, and then you have to figure out what is the the real chemical potential, because it's a mixture of some here. We did it for a homogeneous, laterally homogeneous illumination and generation of photons, and we did it for a spherical one, and you see there's a slight difference, in particular here, whether this here is either homogeneously laterally or it's a point function. How to perform this experimentally, what we have seen here to get access to this data of their quality. We do luminescence. This is a cryostat with a sample. There are different lasers for shining light, and then it's calibrated for absolute photon fluxes, spectrograph, and an optical multi-channel detector analyzer for all the wavelengths in sample. We could also do it with a laser excitation like here, and a little bit more elegant, and it's more comfortable to put the light by an optical fiber to this thing here, and we have a header sample holder to be rotated in different directions, and we put out the light again, and to be a little bit more flexible. The same thing here, replaced by some fiber, put a spectrograph and optical multi-channel analyzer, the same like here, to get the spectral selection. This is one example, and it's in principle, it's crystalline silicon, and you see from luminescence the different action, the different impacts of the passivation layers. And only to show you that this is some crystalline silicon passivated with an aluminum rare contact, which has high surface recombination and different other things, variation of the passivation layers, and you could shift by this different recombination, that rare and front contact, you could shift the luminescence. The temperature is always the same with 300 K, shift the chemical potential due to the increase of the carrier density by more or less recombination at the front and at the rear surface. This is an example how it would work with an excitation from the left-hand side of the sample, or from the right-hand side. You get this red and the blue shift, and the Bose term gives you the temperature. And you see there's a slight difference, so you should be very, very careful. What's the generation profile of the sample? Again, another experiment we did in order to be sure and safe what we are measuring. We illuminated the sample from the rear and from the front side, and showed that there is some difference in the spectral distribution. This is, again, a crystalline silicon. This is a solar cell. And the solar cell is operated for the luminescence, the same steady state for the luminescence, either in VOC or in ISC. And in VOC, the chemical potential is higher. In ISC, it's almost close to zero, because this is thermal equilibrium radiation. If you extract all the carriers and don't give them a chance to recombine. And so we did it for different points on the IV curves, something in between, only to show you that there's a big difference between the two. We also made this for characterizing a microcrystalline silicon matrix with some dye incorporated. This is only an example of what luminescence can tell you. So this is a microcrystalline silicon. There are some dyes incorporated, and this is the organic dye here, the blue one, and we could shift, due to the interaction of the photons with the matrix, the luminescence of this organic dye microcrystalline silicon in comparison to only the microcrystalline silicon by about 20 or 30 millieV. What about polycrystalline material? This is a cross-section, SEM cross-section of polycrystalline copper indium diselenide. Looks like this, and the grains are in the range of 2 or 1 micron. And then it gets a little bit different. If we do it without lateral resolution, then we are averaging these nonlinear independent magnitudes of the luminescence of different places, different locations. So this is a sketch that tells you there are laterally different patterns of photon flux at different temperatures, different chemical potential. Then we do some estimation what's wrong and what is the averaging of these non-linear functions. And that's why we did it with lateral resolution, photoluminescence here in a confocal setup. The important things are in this laser, red laser or green laser, beam splitter that goes via some microscope mirror lens to the sample, and we get the light from the sample into the detector, or the light from the sample on the rare side to the detector, so we could analyze the luminescence from front and rear side. And in addition, for those who are interested in photovoltaics, we can do this also with a monitoring the IV curve of this, if this is a solar cell. With a sub-micron resolution, because we are also interested in a sub-microns, we take a lamp for the illumination, the same thing from the front and the rear side, and we make the check with a IV curve to get a little bit more. Show you what is one of the results of the luminescence in all these studies. This here, and this shows in a 40 times 40 micron resolution at the same phi naught excitation. This is excitation, hundreds of this here. You see there are some features which are repeated here, but the difference here, the spread, the lateral dimension are different. And this is an extract of the 10 by 10 microns with the two thoughts. And the red one is high luminescence, and the blue one is low luminescence. And this is the difference of the quasi-thermal levels. You see there's between 0, it's the difference, it's not the absolute number, it's the difference. So you get 40 milli-eV difference in photoluminescence studies for the quasi-thermal level when you average over these things. It's a huge amount of variation. And on the right-hand side down, you see the number of occurrences of the quasi-thermal. This is the distribution. We do it even with better, with higher resolution, with a cantilever SNOM. And I have learned that there's also a cantilever SNOM available here. So the resolution of the same thing, like I showed you, two lasers and monitoring from the front and from the rear side with a cantilever SNOM with a resolution of about 200 nanometers. And we get some other pictures of this. This is the AFM topology of this sample. And this is the fluctuation of the quasi-thermal levels. And this is the fluctuation of the band gap. So you see there is not really a good correlation between grains and quasi-thermal level splitting, or the variation of this, or the fluctuation in the band gap. That does not mean that the high band gap always have the higher chemical potential. And so this yields that there is a large variation from grain to grain in quality. It's nothing absolutely to do, or only few correlation between the optical parameters of the film, the band gap, for example, and the quality or the fluctuation of this quality. Again, lateral variation of the quasi-thermal level splitting. It's another sample. This is the band gap again, and this is the photon energy in the position. So we make one of these traces here and get the photon energy, the variation of the photon energy versus position. You see this is high photon fluxes and low photon flux is the blue one. And this shifts a little bit forth and back depending on the spot, on the location. This we already had, and now this is it's only to tell you on the right-hand down figure that if you make the averaging, what we do make wrong. If we make the averaging of those things we did with a high lateral resolution, we get some variation of the quasi-thermal levels between 500 millieV and 900. That means 400 millieV is our error we do if we make the average and not the lateral resolution of this magnitude. One of the experiments we did also with a fluorescence collector, which is well known here. There's the fluorescence collector excited by some light, laser or sun or whatever, and there is the excitation of the dye, and the dye emits fluorescence photons, and due to the refractive indexes and the geometrical dimensions here, due to the refractive index from front and rear side of the collector and environment, you get the zigzagging of the photons mainly to the output on the edge of the collector. One of the experiments was that we tried to reduce the emission of the fluorescent centers through the escape cone, which is here, which is determined by the refractive indices of this and this environment and matrix of this to put it back. And the photonic crystal is nothing else but the equivalent of an electronic crystal for the photons. That means there are some steady state calculations for the propagation of light, like for the propagation of electrons in a crystal, in a periodic arrangement of refractive indices. This is here. And so there are some directions of the light that might, for particular photon energies, not penetrate in this direction. And this is what does this photonic crystal, which had been prepared by some colleagues of us in other universities, in particular for crystalline silicon, for the light of crystalline silicon and for the light of a fluorescence collector with a rhodamine 6G. So we analyzed this with the light that came out with and without the photonic crystal from a doped rhodamine 6G doped sample, and we did this in the detector, and we made this same experiment in varying the entrance angle and varying the exit angle of the light that comes out. This is an example of the light that came out from, in the upper part, from a rhodamine 6G doped fluco versus detection angle and wavelength. And this is with a photonic crystal. You see there's missing something here. And this is what the photonic crystal blocks. And this is the difference. And the same down for a differently adjusted photonic stopgap for crystal and silicon. This is an absorber, the light that comes out versus angle and wavelength. And this is with a particularly adjusted photonic stopgap in crystal and silicon, and this also changes. So you see there is a dramatic reduction of the light that goes through the escape cone. And this is also done by some luminescence fluorescence studies. So this, what I told you, should have been an advertisement for looking at the light that comes from matter. And this light tells you some state, tells you temperature, tells you excited state, tells you quality of the material. And I like to add once more that if you are interested in the view graphs, they are available either in my USB stick or at Professor Marquardt. And if you like to get some more knowledge about what we have done and what my former expertise in photovoltaic things is, then you could get a copy of the PFD version of something which results from Oldenburg. This is about my thinking. There's a copy of in a PFD version available, and I let this here for your library in the group of Professor Marquardt, and I thank you for your patience. Electroluminescence is it's a hard method. It's very, very hard. You bang electrons in, and you heat, and you damage. And our method is advertisement. It's soft. Yeah, you don't do but shining light, which is the normal function of a solar cell. So it's the same. Like you illuminate by natural sunlight. It's not entirely true, because you need some, for the confocal things, you need more flux than the sun will provide for you. But electroluminescence, what do you see by electroluminescence? You see an excited state that is far away from that state that is created by solar light. Yeah, it's like touching a lady or giving from a boxer a hit to somebody. So electroluminescence is a rough method. You see the fine details, but under illumination with electrons, which is much, much, much above the normal level, the regular level of sunlight. I go back. You tell me which one. It was crystalline?
I think it was the crystalline silicon, I think the spectrum. It was somewhere. Yeah.
Now this is how to analyze this. This one? Or
It's self-contained. It's the shape which has come up on a number of occasions. It's really one part which is completely reabsorbed, and one part which is not reabsorbed at all. And can you say something? And then you said something. Photon recycling is completely neglected.
yeah, this is it's yeah. For crystalline silicon and for this copper indium diselenide stuff, and not for gallium arsenide, but also at the very beginning we made studies on gallium arsenide, and that's why I didn't show this. In crystalline silicon, microcrystalline silicon, copper indium diselenide with all these variations with the indium content and so, photon recycling is negligible. Not in gallium arsenide. Then it means in direct semiconductors like gallium arsenide, you have to be careful. And I didn't show the figures of gallium arsenide.
Yeah, would you say, I mean, the copper indium diselenide is also direct silicon?
We neglected it, let's say like this. And there was no, at that time, there was no information that we should put it in.
Silicon, I would agree on it.
Yeah. And we certainly included it in this fluorescence analysis. This is the reabsorption and potentially photon recycling. There it's in, but we did not discriminate this reabsorption and photon recycling. We only looked at but we thought that it's included. And for the audience, I like to add a crazy. It sounds crazy, but it's true. It's really true. You take a solar cell under sunlight, and it works. And the more light that comes out, the better is the solar cell. I hope you agree. And if not, we could discuss this.
No. Can we ask by show?
It's not an examination.
So, why? Because quite an interesting topic, because some people got recently have claimed it as their discovery. They have rediscovered the, well, not the wheel, but the luminescence from solar cells. That's a different story.
So another provocation. It's even Tom would not agree entirely. If you take a traditional crystalline silicon solar cell, and there's an illusion, the band goes. I try to show the conduction band edge and the valence band edge. So this is the conduction band here, and this is the valence band. P-N junction. And some people even today think that these electrons here in the space charged region would go down here due to the slope, like these people that go for downhill skiing on the Zugspitze or some mountain in Czech Republic or Slovak Republic. And this is not true. And as I plotted it here, I'm certain that nobody of you could tell me whether the electron goes down or up or doesn't move. I've not used the term electric field. I've only asked, what does the electron do?
Electric field is there.
I don't.
Can I ask you, if you take an apple, which I believe
Yeah.
if you drop it, what happens?
The apple gets some defect and falls, and then because the mass is so large that the thermal energy of the apple is not enough to go against this distance.
Rephrase it, because the density of the upper material is higher than the density of air, which means the upper falls attracted by the field of gravity. That's what we learned in school. I don't know if it's true, maybe it's
I would like that, not the field. I would like to take, like Einstein also proposed, to take the potential. It's the gradient of the potential.
gradient of the potential. It always falls down.
Not always, not always, not always. I could imagine that the apple, which is composed of a lot of atoms and molecules, with all the vibrations, that at one moment that is in the phonon frequency range of 10 to the minus 12 seconds, imaginable, all the molecules move upwards for 10 to the minus 13 seconds. And we have to look at this, and it's very, very unlikely that we see it. But then the apple would go up, even if it's laying down.
For a child, or somebody who looks at it with the naked eye, the apple falls. Now, I will put it to you that what you have at the junction is a similar. What you drew, what you say you don't see the electric field, is either
This year, it's open. It's.
What you forgot to show him, he quite complete.
It was by purpose I did.
When you illuminate the solar cell, suddenly you've got a very high number of electrons being created by light.
Yeah.
Very high density electron gas, which are like the upper, and which will then, there is of course a small, in equilibrium, this current, this flux would be compensated, but under illumination, you've got high density electronic upper, which will fall down the slope like the upper does.
It reminds me an example. There's certainly a high mountain here in your country. And there are some little molecules, let's say nitrogen. I exclude oxygen. And due to the slope, they all will go down. And after a while, there is no more nitrogen. And even oxygen, I don't want to make it with oxygen because it's dangerous. Then all the molecules are down. They are here in the valley of Prague. Or they are, even if they are wise, they go to the Dead Sea because it's even deeper. So in this case, the electron, depending on the Fermat level here and there, will either go down or go up, then it's a luminescence diode, or will stay here and doesn't move because except Brownian motion. So with that, without the Fermi level and the quasi-Fermi level, nobody can tell what the electron does.
You cannot tell for individual electron, but you can tell
Ensemble.
electron flow, which manifests itself in the electron gap.
I make the one electron approximation which holds for all the electrons. And should we go into the discussion of correlated electrons? I'm not firm in correlated electrons because this is.
As long as you can observe electrical current, you know that there are electrons falling down the hill. And
If
argue that it is because of the electricity, because the current always flows the electricity.
but
Never flows up.
but
In the upper, it would never go in the field of gravity.
in average, the electron in a luminescence diode go up and then recombine here, and if not, then you wouldn't get light out. It's
Then you do, it's not excited by high density of electrons, it's really more similar to buoyancy that you can move.
You're right that if there are lots of electrons here in the excited state, then they go, due to the gradient of the electrons here and here, go to the gradient in density, to the potential. There are lots of physical experiments which cannot be explained by field. So even in the Hamiltonian, it's not written a field, it's the potential. Yeah? Then we take the potential, and this is the chemical potential. The chemical is the most general, not the most, but for experimental physicists, the chemical potential is the most general magnitude that tells what species do in chemistry, in physics, and even in electrical engineering. It's by purpose that in the Hamiltonian, it's not the field, neither magnetic field nor electric field nor gravitational field. There's the potential in.
I will introduce another term which will deviate from the Hamiltonian, because what you're talking about, the reason why you are saying the electrons don't move, because the chemical potential is constant.
Yeah.
But there's a term, only one term is the gradient of the electrostatic potential. The other term is the gradient of entropy, which is a thermodynamic force, which acts in a different way.
Yeah.
I was going to say, before we get into we might stay here for a little bit longer. And, rather than acting as two actors on a stage, I would invite anyone else to contribute. And if not, then we can adjourn. We're going to
Yeah.
But you are all invited to participate. So this is a discussion that has just been going on for many years in various places, and which are also invited. And obviously, you see, it's not
Let me add, because when I was younger, and I used to have the last word. Let me add another illusion which is widespread. This is field emission. You know, there's the expression that a metal, if you apply a high electric field against a metal and an electrode, you get electrons out. I have learned this when I was a student, and I thought I'm too foolish to understand what happened. This is the metal. This is vacuum. And there's some electrode, and you take a high voltage source, and people say that they are coming, and if you make a tip here, some geometrical tip, then it's easier, then you get electrons out here. Okay, if this is an ideal metal, then electrodynamics and the students in electrical engineering, they have learned, and they believe, and probably it's true, that in an ideal metal, there is no electric field because it's ideally conductive. So the electrons are in the metal. And if there is no electric field, how does this electric field get access to the electrons that are in? Because there is no electric field inside. Well, it's a dilemma. Or is it only that way that you put the energy level, and this is the work function of the metal? You bend this, or the other direction, excuse me. You bend this by electric potential, and you decrease the barrier, and the electrons come out because they feel that the barrier, the potential barrier, is lower. Now, I stop my emission reaction now.
I don't know enough about the field addition, but we can carry on about the
Yeah.
what moves the electrons and what separates the charges.
Yeah, I'm a fan of this potential because I like Hamiltonians.
Only one term you can explain in terms of Hamiltonian. The other term, in terms of potential, you can only explain by thermodynamics.
It's right. But think of these two slit experiments for electrons with a magnetic field encapsulated. There is no magnetic field acting on the electrons, but there is the potential of the magnetic field, and this makes the interferences. So that the magnetic field in this coil is outside is zero, and the electrons feel this, and they feel this the vector potential of the magnetic field.
Discussion is being recorded.
Okay.
Does anybody else have any comment to make?
Yeah. You see that in this Bose term that is valid for photons, this is the h bar omega over the exponential function, the -1 here. There is the E, F, or the h bar omega minus mu over kt. And you make this positive, this expression gets smaller and smaller and smaller, and this pops up. And you make it negative, then this gets larger. And in comparison to the thermal equilibrium, Planck's radiation, you get less out. It's theory. And you wanted to know how to do it? Experimentally? So I'm going to make it a little bit more, not so easy. Thermal equilibrium, semiconductor, intrinsic semiconductor, okay? Well, that's a little bit more. Fermi level. Conduction band edge, valence band edge. This gives, by generation, thermal generation, and recombination, and forget about the stimulated, the Planck's law. How to get it less? Not by temperature, by pulling out. You take the electrons out, reverse the diode. And then you get less light out because the space charge region gets less occupied by electrons and holes. And we tried this. I was so enthusiastic that we tried this.
You can also do it by expansion in the direction. By, for example, you imagine some some material that will actually retain the temperature. You retain temperature source. And you absorb it from a very narrow angle, and you absorb photons being emitted in the hemisphere at the same temperature. These photons, because you've expanded the number of states, these photons...
Yeah, then the density goes down. We asked the colleague of the crystalline silicon semiconductor stuff in the Faculty of Electrotechnical department in Berlin, and he made us a crystalline silicon diode, PIN, crystalline silicon, which is very rare, you cannot buy it, with a very, very thick eye layer. Because to get a large area for emission, to get a large signal. And we did it in reverse direction. And we saw nothing. And why? Because the thermal radiation of the environment is so high that we couldn't see the teeny effect of this luminescence. So it was the luminescence signal looked like this. And when reversing, it looked like this. This is omega, and this is the light flux. And it was so pity, and we were too foolish. We were too foolish, and the student gave up at that time. We were too foolish to increase the temperature to get things like this, and then to make the same experiment. And so we missed to show that we get less photons than in the Planck's law. It was a pity. I got very, very angry when we realized that we did it not in the appropriate way. Yeah. So the message is there are a lot of little problems. If you think in detail and very seriously, you get a lot of misunderstandings, a lot of illusions, and a lot of bugs in all our explanation. So don't stop being critical and don't believe. Try to understand. I left this here for Tom. It's yours.